Hello, hello, good afternoon. Welcome to today's session. It seems people joined lately today. We're starting a little behind schedule. Once again, my name is Ridwan Salahuddin. So I'm glad to be taking you through this program. We've gone so far. We are in the fifth weekend, I beg your pardon, and that happens to be the 9th day, and tomorrow will be the 10th and final day. So far we have learned a whole lot of things about data science fundamentals, ranging from understanding what the term data science is, to understanding some of the tools that are used by data scientists, which include but not limited to NumPy, Pandas, Matplotlib, and last weekend we had our introduction to predictive modeling, so where we discussed on the first weekend, the first day of the weekend, we discussed types of machine learning algorithms, and the second day, which was on Sunday, we discussed understanding learning algorithms, and we focused on linear and logistic regression. So today, we'll be discussing further about logistic regression. So logistic regression is one of the oldest non-machine learning algorithm. It has been around for a very long time, and it has proven to be very powerful and efficient. So I'll talk you through some of the things that makes it quite exceptional. So in the industry, so a lot of times it is not just of interest to be able to forecast or classify or predict things. It is equally important to be able to explain the forecast, how the learning algorithm came about the forecast. And from the class we had last weekend, I was able to show, so if you, okay, sorry, I had a break in connection. I'm back. Okay, so I was saying that from the discussion we had in the previous class, so I showed at a very high level how logistic regression is built, logistic regression algorithms, how they are built from scratch using simple linear equation. So y equal to mx plus b. So, and simply finding the m, which is the slope, and b, which is the intercept. So although in machine learning, we don't usually say mx plus b, rather we say wx plus c or plus b, yeah? So wx, so the w being the weight, and b or c, as the case may be, being the y-intercept. So we showed that, okay, by calculating this slope, in the case of whether it is just one variable, one predictor variable we have, or multiple predictor variables, in which case it will be multiple regression. So it's still the same thing. We only need to know what the W is, or what the W's are, when there are more than one variable. So today's class is going to be brief, and the essence is to give ample time to ask questions. So I know last Sunday's class was relatively, should I say, was packed. So it was quite packed. So last session was quite packed. So I'm going to, as much as possible, to answer questions we have from the previous class. So if you have questions from what we discussed in the previous class, you'll be free to ask them today, because what we'll be doing today is going to be built up on what we did last weekend. So the only additional thing we'll be doing today is we'll be talking about metrics in machine learning. We'll be talking about how to improve our model, and I'm going to walk you through the thought process of building, or maybe should I say, building a predictive model from the start to the finish at a more detailed level than we had last weekend. So you're going to see me from importing the modules to reading the data sets in, to from start to finish. We're going to do just that. Okay, so I was talking about what makes linear regression very linear, or logistic regression. Both of them, they actually build up on the same fundamental. Okay, so the fact that it's simple linear equation makes for easy explainability. So you can easily say, okay, because there's a strong correlation between this variable. So by variable, we understand what variable means at this time. So that's, okay, this variable or this attribute or this particular thing, there's a relationship between it and this other thing or this other event. So when we have such, it's very, very easy to model it as a linear, a linear model. And that's what linear regression or logistic regression thrives on. So this explainability makes it a popular choice in industry, where they want to be able to explain the decision made by the machine or the algorithm. So apart from that, it is extremely fast. And I say extremely with emphasis. It is extremely fast. So easily, if you're running like linear regression, if you're running linear regression on as much as 1 million records, it gets done in few seconds. And when I say few seconds, very few seconds, probably within 2-3 seconds, it's done running. So linear regression or regression algorithm, regression-based algorithm, sorry, yeah, I should still say linear-based algorithm. Let me just put it that way. So linear models. So linear models are actually quite fast. So that's a big plus to linear and logistic regressions. Okay. Now today, like I have said, we'll be doing more about logistic regression. So we have a data set to play with. So I'm going to show you how I sourced for the data set. So like I said, today's class, so feel free to stop me at any point through this class. Okay, so I sourced the model by simply going online and doing, okay, data set search. So Google has a data set search platform. So this is it. So you can see it's titled data search. Data set search, I beg your pardon. So I just put in, okay, logistic regression. So, and it's going to bring a host of results. I don't know why my internet seems to be quite slow today. Okay, so you can see the first result I have here is logistic regression to predict heart disease. So I simply opened it, and the data is hosted on Kaggle. So I have it downloaded already, but I'm trying to open it so we can see the description of the data set. So, and just in case we're also looking for data sets to play with, we can do just the way I did. So here we have the description of the data set. You can see if you've never used Kaggle before, so maybe in one of our next programs that we'll be organizing, one of the tasks will involve Kaggle competition. So hopefully I'll introduce a lot of us into to Kaggle and how to participate in competitions there. So here we have data. So this is my account. You have to create an account to be able to access. You can access it with an account, but you can't download. So I have an account and this data, so I can create task here. So I'm not really going deeply into that. So what I want to see is description of the data. So it tells us that this is the title, then introduction, world estimation has estimated 12 million deaths occur worldwide every year due to heart disease. Half the deaths in the United States and other developed countries are due to cardiovascular diseases. The early prognosis of cardiovascular diseases can aid in making decisions on lifestyle changes in high-risk patients and in turn reduce the complications. This research intends to pinpoint the most relevant risk factors of heart disease, as well as predict the overall risk using logistic regression. So now the person that uploaded this data has done some analysis, and we can see his result here based on his analysis. So, but what I'm going to copy is the description of the data set we have, which is this. So I have already downloaded this data set, and I'm going to share the link to access it with everybody as well. So I'm going to put this here. So when I upload this, yeah, oh. Sorry, I got disconnected once again. Okay, so the data is grouped into demographic, behavioral, medical history. I'm trying to make it properly formatted. I'm still going to format it for that before uploading it. So you're going to get something that is well formatted. Okay. And finally, so I'm going to bold in some beg your pardon. Okay, so what we have here is the description of the data we'll be using today. So just a moment while I copy the data from where I have it. All right, so now, so this data, let me give a little more background to it. So the goal of this data set is to be able to predict outset of cardiovascular disease. So a long time before it actually occurs, as we can see here. So now we're giving demographic data. That's sex, age.
Sorry, we can't see the screen.
Oh, sorry. Okay, sorry about that. So we have the demographic data, we have the medical history, we have the medical current, that's the current medical condition. That's including total cholesterol level, systolic blood pressure, diastolic BMI, heart rate, glucose. Yeah, so many. Now, so this is a typical use case. This is a typical situation where machine learning can be especially useful. So you would imagine that if, okay, so let's look at the predict variable desired target here. So what we are predicting is 10-year risk of coronary heart disease, CAD. So binary 1 means yes, 0 means no. So this is what you're predicting. So 10-year risk, that's to say from today, 10 years from now, what is the chance that this person with this medical history is going to have coronary heart disease? So what happened? You may wonder, okay, how did they get this label? So what they will typically do is they have some patients who, so maybe they have their record as at a particular time, and 10 years down the line, they found out that, okay, they have this disease. And there are others too that 10 years down the line, they didn't have it. So that's the way they got these records. So let's assume the way you regularly go to the hospital for checkups, and all these things are logged in your medical file. So, and as today, assuming today is the cutoff date used, so as at today, all the records you have as at today, including the previous records you have, so they will be held constant, and they will now watch you 10 years from now. Do you have this coronary heart disease or not? So, and that's how they got this target label. So now what we're predicting is 10 years down, anybody for whose record we're able to get, can we predict whether this person is going to have coronary heart disease? So this is typically going to be useful, because if this model works very fine and it predicts accurately that 10 years down the line somebody is going to have this disease, so it's very easy to encourage the person to make changes to diet, for instance, to make changes to lifestyle, to maybe start taking other preventive measures. So, and this is what makes it especially useful. So, given this background, so let's now proceed to start out building this model. So typically what you would do is you'd import the tools. So here we know we would need Pandas data frame to read in the data. We may need NumPy for numerical processing. We will need matplotlib to plot our data. Matplotlib.py plots as PLT. So we also need sklearn library. So we'll import it. But sklearn has so many modules in it. We have to know the particular modules we'll be using and import the particular functions or methods from those modules. So here, I know we'll need to split our data into train tests. So I'll say, okay, from sklearn, import sklearn. I'll say from sklearn dot model selection. So model selection module is the module that contains train test split. So don't despair if you can't remember all these things. It's very easy to go on the internet and say how to split data into training and test. You can see the suggestion there and you'll get it. So here, model selection, import train, and a lot of times if you start typing and you've gotten the first few words correctly, if you simply tab, it's going to complete it for you. So should you not remember whether there's a space in between or whether how is it spelled and all that, it's okay. It's not something to worry about. You can easily, like I said, do a Google search or make use of the auto-completion option that Jupyter Notebook or other IDLEs provide. So I'll also import logistic regression from linear models. Linear models, import logistic regression. So what else do I think I'll need? So I can think of others, but I'm just trying to make it look typical of how a lot of people will get started. So I'm going to leave out other things that I would need, and as we go on, as the need arises, we'll come back and add it here. All right. So let's have those imported. So it's still running. Module not found. Linear models. No module. Okay. I think it's linear model instead. It's linear model instead. Okay. It's fine now. So we'll read our data sets in. So the data set is stored. Let me show you how the data set is stored. Okay, so the data set is stored as framingham.csv. Although I'm going to upload it to GitHub, so I'm going to provide a link. It's still going to work if you make use of the link instead. So let's call our data, and we say pd.readcsv, and this, beg your pardon, framing, trying to get the spelling right, framingham.csv. So data.head to inspect it. So there we have it. So we have the first 5 records. Now, after importing your data like this and inspecting it, at least we've checked the head. We may also want to check the tail, data.tail. So assuming I want to check 10 instead, I don't want to check bottom 5. I want to check bottom 10. This number can be anything. I can change it to bottom 15. All right. So let me make it bottom 10. So I've seen the bottom 10. I can easily see that there's a none here. There's another here. There's another here, which means my record has none. But more appropriately, I'm going to inspect it. So here I'll say check, inspect the data set for nouns. So how do we inspect data for nouns? There are 2 approaches. You can just say data.info. Data.info will give us a summary of our data. So we can see that we have 16 columns here from index 0 to 15. The number of records is 4,238. Then each of the columns, you can see this one has 4,238, while some have fewer records. However, to guess precisely how many null values we have, so I'm instead going to, so here this one also tells you the data type. You can see some are int, some are floats, and this data looks like almost ready-made for linear logistic regression. All right, so as usual, few minutes from now, we will have to break and reconverge immediately, join the meeting back immediately using the same link. All right, so let's guess precisely how many nans. I mean, it's more difficult for us to figure out how many null values are in each, except we want to start subtracting one after the other. That's clearly inefficient. So, but Pandas provides a very nice method, isNA, which returns a mask of true or false values. We can see true, false, true, false, true, false. So, however, we want to know how many truths are there, how many for each column, how many true values are there. So, simply say sum. So, typically, Python interprets true as 1. So, when you call sum on a data set that has that has truths in it, it's simply going to add the truths. Okay, so we can see that education column has 105 null values, BP meds 53, and others too, glucose 388. That's like the most significant. So what do we do next? Now we know that we have some null values. And logistic regression does not support null values. There are some models that support that can handle null values, but definitely not logistic regression. And most models actually don't handle it well. All right, so now we know that we have some null values. What should we do to fix these null values? But before that, let's also get the summary of our data by doing describe. So let's see the distribution, the mean, and all that. So I'm going to turn this around by calling transpose. So I can have these columns on the row side, while these rows on the column axis. So transpose. So this is much more readable. So we can see male has these counts, age, and all that. All these columns have their counts. The mean value. So mean, well, it took the mean of sex, and sex is simply 0 or 1. 0 being female, 1 being male. But it took the mean anyways, but that's really not going to be useful. But the good thing is we don't have any null value there. So age, the mean age is 49.5. The standard deviation is 8.57. So this tells us that most people are within the age 41 to 57. Yeah, so most people are within the range of 41 to 57 based on the standard deviation. The minimum age is 32. You can see it makes sense. The first quartile, 42. The median is 49. The third quartile rather, 56. And the max is 70. Okay. We won't waste much time investigating this further. So let's simply move on to visualizing our data. So I've not forgotten that we have some null values here that we have to deal with, but let's visualize the data before making a decision on how to handle our null values. So we're going to do box plots. So box plots, let's try to see whether we have some extreme values. when we discussed plotting, I mentioned that box plots is especially useful to see how your data is distributed, whether there are extreme values there, outliers. They're typically called outliers. So I'm going to loop through my data for column in data. So data dot box plots. So plt dot title. So give it a title of, say, plot of all. So this is simply going to say plot of, and whatever this column is going to substitute it with s here. Substitute you to substitute this s with it. So, and I want to show each of it. Plot.show. All right, so there we have it. So of course, we don't expect anything on plot of male. I mean, whether the sex of the person is male or female. So if it is male, it's simply 1. If it's female, it's simply 0. Plot of age, we don't really expect. I mean, sorry, we really expect much from there. So we don't really have any outlier here, as we don't see anything beyond the max here. So if you had seen, I mean, beyond this, the max. So if you had seen some records beyond this mark here, then we can easily conclude that there are some outliers, or below it even. So we don't have outliers here. Plots of education. So can as well see that the median age here is about 49, which is in agreement with what we saw earlier on. So plot of education. So let's see. So if we come here, you can see plot of CIGS per day. So if we check what CIGS is, see the number of cigarettes that the person smoked on average. So we can clearly see that there are some people that smoke so much that they are considered outlier. We can see somebody smoking 60 cigarettes per day. Is it packs? Let me go back and check. Number of cigarettes. Okay, so it's number of cigarettes. So we can see somebody smoking up to 60, another person smoking up to 70. And I mean, clearly this is abnormal. So, but it's possible that it's valid. So we don't really need to make any decision. In some cases, there may be need to, when you see highly extreme data appearing, so there may be a need for you to maybe trim those extreme values and put it at a reasonable range to avoid skewing the data you have or affecting your model negatively. Okay, so next, plot of BP and all that. So we can see this is also showing values between 0 and 1. So we don't really have much to infer from here. Okay, so plot of total cholesterol. There seems to be so much outlier here, or so many outlier, let's say. And okay, systolic BP and all that. So this is just simple. I think it's just, I mean, it's not everybody that's, there are not many people that have these cases. And that's why those people that don't fall into the general distribution, they will be called outliers. They return outliers here. So what I mean is, maybe most people, yeah, there are people that typically have maybe, let's check this total cholesterol level. So we can see the median is about 220 something, or I mean, about 230 something or 240 something. So, but we can see people in the region of 350, 400, 500, 600, 700. these 600 and 700 may actually be outliers. They may be errors in imputation or something, and they may also be valid. So, but people falling in that spectrum is rare, and that's why this thing is telling you that, okay, these people are likely outliers. So these are the ways you interpret your plots. Should you wish to, so if you look at this, especially this one, plot of glucose level, I mean, it's just so many seems to be outliers. So many beyond the marks. So many outliers we have there. Now, having plotted, there are other plots we can create. We as well want to create scatter plots to see how some variables and others, how they correlate using your scatter plots. Then we may also want to see, yes, the target label. What's the distribution? It's very important. So I'll plot data.head again. So these are target here, 10-year CHD. So let's see plots. Column, kind, bar. I beg your pardon. X must be label or position. So I think I'm supposed to include this. Okay, this is taking too long. Let me just put it this way. I wonder why it's taking so long to plot. So I'll simply use NumPy, Pandas plots. I beg your pardon, Matplotlib plots. PLT dot. Okay, it's coming out. So I don't expect it to. Okay, I think I figure where the issue is. I'm going to do a value count first. Value count. So we can see the value count. So this is what we are plotting. Values. So values dot plot kind bar. Yeah. So we can see values with, 0 targets are very, very many there, while the target value of 1 is relatively fewer. So this is what we call unbalanced data sets. Right, so it's worthy to note that, okay, I think our time is almost over. We'll have to stop soon and resume back. So I'll quickly mention this. In most real life Okay, so welcome back. As I was explaining, in most practical scenarios, you will be dealing with imbalanced data sets. So let's look at this scenario. People that have cardiovascular disease. So are there more people with cardiovascular disease than people without it? You'll agree with me that it's a no. So you're more likely to find people without cardiovascular disease than people with it. And the fact that even people with cardiovascular disease may not always report as well. So their record may not be available. If we look at the field of, let me think of another field where imbalanced data sets is rife. So let's see an example. Assuming you're trying to predict whether a transaction is a fraudulent transaction or not. So you know that typically most transactions in anywhere, whether you're running online business or you're a bank or any institution. So fraudulent transactions are usually fewer than normal transactions. Before you can have one incident of fraudulent transaction, you would have had maybe thousands or even hundreds of thousands of normal transactions. So you have to know the strategy of dealing with imbalanced data sets. I'm going to showcase at least one here. Okay, next thing to do is, okay, let's start modeling our data. But if we decide to model and we have nons, null values, the model is not going to work. We're going to get error from it. So we have to handle our null values. Remember, there are different ways we can handle null values. We can handle null values by filling with fixed value, maybe 0, for instance. We can handle null values by filling with maybe the median or the mode, or so sometimes it's having knowledge of that field you're predicting or you're building model on helps to make decision. So you may want to use mean in some instances, while in other instances you may want to fill the null values with median. So what do I mean by this, in case it's confusing to you? So if we have generally, like, sorry, my connection was lost. Excuse me. I'm trying to find, okay. All right. Now, if you have cases where some patients' ages are not recorded, so you might want to say, okay, should I use the minimum age to fill for those people, or should I use the max, or should I use the median? How about I use the mode, the most frequently occurring age? Okay, how about I use the mean age as well? So it could be any of these. And as well, it can also be random by saying, okay, use a forward fill or a backward fill to fill the missing values. So we'll err on a simple side here. We'll simply use forward and backward fill to fill. It might not be the most ideal, but at least it's going to work for us here. So what I'm going to do is I'm going to look through the columns in data, and okay, so it's also worth mentioning that if I fill values that are none, the moment I fill any value in for those null values, I have lost the information about it being null. And that's like throwing away valuable information. So one approach to handling such situation is to create another column. So for instance, let's assume we're talking about age here. And we now find out that there are some records that don't have age, some patients whose age is not captured or whose ages are not captured. So instead of filling up the ages alone, we want to at least have another column that tells us about that column, the original column. So whether this record had its value filled or was a null value before we filled it. So it typically improves model. So what I'll do is I'll first run this model without doing that, and if we have enough time, I'll now run it again by doing that. So here we'll fill now with forward fill, and we also do backward fill. So remember why we have to do this, just in case in the case of forward fill, it will fill with whatever is ahead of it. So that's forward fill. Backward fill, it will fill with whatever is before it. So we can have extreme situations where the first record is null or the last record is null. So to handle that, we have to use both forward fill and backward fill. All right, so I'll simply say data call equal to this. As I loop through the columns of this data, I'll do this. All right, so if we check now, data.isNa.sum, we won't find any null value again. Another approach is to simply drop the null values. Any record that has any null value, drop it. That's another approach. If we choose to use that approach, we'll be losing so many records. The time I tried it would lose up to 12% of the records we have. So we have over 4,000 records and we'll be losing over 400 records if we decide to drop it. So sometimes it's a go-to option, but in most practical situations, it's not advisable, because what that means is, what if you are faced with those situations that have null values? Are you simply going to say you can't predict for those people? All right. So next thing is, let's proceed to build our model. We have to first split our data into train and test. So let's say we have train and test. Remember, we imported train test split. Train test split. And we'll pass in our data and we'll tell it that test size so we can specify what we want this the size of the test is, what we want it to be, I beg your pardon. So if I want it to be 20% of the data, I'll say 0.2, or 25, 0.25. All right, excuse me. So we have to specify test size. Now, let's see our train.shape, test.shape. So train.shape is 317 by 16, test.shape is 1060 by 16. So next is to go ahead and make our prediction. And build our model. So let's say model is equal to logistic regression. So these are model we've created it. But can we just simply go ahead and fit the model without separating the target value from the other predictor variables? Of course, no. So we'll go back and do that. So we can say train.x equal to what? So let's say train.x is train, but we'll drop the target label from it. So target label is this 10 years CAD. So we drop it, it's on axis 1. We can say train y equal to train. So this is the train y, right? So but we have dropped it here. So we'll do the same thing for test. Test x test dot drop axis and test y test. All right, so this is going to split is going to separate the target label from the predictor, the target column from the predictor variables. So next is to fit our model. So model.fit. So keep in mind that we've not done any pre-processing to the data. So they are in the original form. Age ranges from 35 to 70. Sex from 0 to 1. There are some values that range from less than 100 to about 700. So the data is not scaled in any way. And we're going to observe something with that. So train X, comma, train Y. So this is what is going, the model is going to train on. So train, yeah, so there's a message here. If you read it, it tells you that LBFGS fails to converge. So this LBFGS is the optimization algorithm. So it is what the model uses to train and update itself. So it fails to converge. Failing to converge means, yes, a model is said to converge when the error is minimum, is at its minimum that it can be. So if it doesn't get to the minimum, they call it global minimum. So if it doesn't get to a minimum, then we'll say that it fails to converge. So there are a number of ways you can address such situation. You can increase the number of iterations by, if you come here, if you check this, so there is max iteration. So the max iteration is by default 100. You can as well change it. Okay, you know, the way algorithms work is they run iterations repeatedly. So it does something, it gets a very bad estimate to start with, then it starts improving on it by running it over and over, correcting the error it made based on how whatever measure it got from the previous iteration. So here, let's assume we change it to 200, and let's see whether it's going to, it's still the same thing. 500 is still the same thing. So clearly, this thing is not going to converge, even if we continue to increase the limit. But there is still another option it gives, and that is to scale the data, increase the number of iterations, or scale the data, and it gives you a link that you can use as guide. Please also refer to the documentation for alternative solver options here. So instead of using LBFGS, there are other solvers that you can use. So let's just try it, just for knowledge, whether any of it is going to. There is yes, there is Saga, and there's also Newton CFG. So let's try Saga solver. Let's try SAG first. So it also did not converge. Saga, same thing. Newton CFG, sorry. What's Newton CG, sorry. Okay, so let's see. Oh, I put new team with M. Okay, so this one works without giving the error. Okay, so let's proceed with this first and see what we get out of it. Now we've basically trained the model. So now let's test it and see how it performs. All right, so we have to now say model.predict. We'll pass in our test X, and that's all. So we get our predicted output here. So did we import accuracy measure? No. So like I said, as we proceed, anything we remember, we go back and fix. I'm going to minimize this to okay. So from sklearn.metrics, import accuracy score. So I'm going to import other things as well. F1 score. Like I said, I'm going to talk about confusion metrics as well. Confusion matrix. So if we're unable to talk about these ones today, we'll do that tomorrow. So this may be the last problem we'll be taking before we get the final capstone project. So the capstone project, you're going to have 1 week as well to complete it, and it's going to capture everything from the start of this program till the very end of it. So, and recall. So these are some of the metrics that we measure, especially in classification problems. Okay, so here I'm going to measure the accuracy by passing prediction and test Y. So we can see without doing much, we're able to get 84.5% accuracy. But this looks good. This looks good until you dig deeper before you can be sure of how well your model is performing. Remember, I imported other metrics. So let's check the recall. So recall at a high level, I think tomorrow we'll dedicate tomorrow to discussing this. Time is already fast spent today. So at a high level, I'm just create test Y. So our recall is 71%, but let's check our F1 score because, okay, did I import precision? I'm supposed to import precision as well. Precision score. So I'm going to explain what each of them means in precision score, read, test Y. So we can see our precision score is very, very poor. And I'm going to explain the implication. So F1 score, read, test Y. We'll be ending the class soon. F1 score is also very, very low. So assuming you don't understand any other metric, you should take note that F1 score, if your F1 score is low, then your model is generally bad. In conclusion, so we can see here that accuracy is high, recall is low. I mean, recall is still okay, but precision is low, and F1 score is also low. So should you not know how to interpret anything, you should at least know that if your F1 score is low, this is 15.5%, your model is generally bad. So this tells us that the model we just built is bad, is performing badly. So now, when your model is performing badly, does it mean that you'll give up on it? No. You'll go back and work on it again. So building a model is not a one-sitting thing. It's not what you sit at once and complete it and just say, okay, you're done. Except if it is a toy project. Yeah, with a toy project, you can get that done. But for real situations, you'll be faced with a lot of things. And I would even say the data we have here has been presented in a very nice format for us. We don't have any text data. We have all numerical data that we could start working with. So lastly, I'm going to get the confusion matrix. Read test Y. So using this, now, let me show you what confusion matrix refers to. Confusion matrix. So we know how to interpret it. Okay. Now, this is what confusion matrix looks like. And if you look at this, it's also a grid that looks like this. So our predicted values are in the on the column axis, and the actual values are on the row axis. So in this example here, the number of records is 165. Now, there are cases where we predicted that the output is no, and it turned out that it was actually no, so that's correct. And there are situations where we predicted the output is yes, and the actual is also yes, which is 100. So that's correct. So this looks like a very good model. Predicted 50 and actual is also 50. Predicted 100 and actual is also 100. And there are also other situations, this other diagonal, where it predicted no, but the actual is yes. And there are 5 instances where that happened. Or here where it predicted yes, but the actual value is no. So these 10 records here were wrongly predicted. Now, accuracy will simply be 50 plus 100, which is 150, divided by 165. So let's transfer this to what we have as output here. So our predicted is 881. We predicted no 881 records were predicted as no, and they were actually no. I hope we're following the logic. Then we have another 15 here. I'm reading this. 15 here. They were predicted as yes. That's they're going to have this the heart disease 10 years from now. And these 15 were correctly predicted. So that's yes and yes. But at the same time, there are 158 that are predicted that as going to have this disease 15 years, 10 years down the line. But in actual sense, they didn't have it. That 10 years down the line, 158 people are going to have it, but they didn't have it. And that's obviously a bad prediction. And there are also another 6 that are not going to have it. I mean, that are going to have it, I beg your pardon, but are predicted as not going to have it, if you go by this grid here. So now, if this model has predicted up to the total people that this model predicted as going to have this disease 10 years down the line is everybody on this column here, 158 plus 15, whooping 173. And out of the 173, only 15 were correct. Now, would you say this model is good? Clearly, it's a no. Because if you predict 160 something people or 170 some people are having a disease and only 15 ended up having the disease, then clearly your model is not precise. So let's come to precision here. So what precision measures is, okay, you said so number of people are going to have this thing. So in this case, 15 here. Let's try to calculate it manually. So 15 are going to have this, 15 plus 158 are going to have this disease. But how many of them truly have this disease? 15. So when you divide this, you get precision. Do you see that the value I got here is the same as the precision score here? Now, this is how precision is measured. So you said this number of people are going to be predicted as positive. Yes, they're going to have this disease. So how many did you get correctly out of all? That's a simple explanation of what precision is. If you say so number of things is going to happen, how many of it are correct? If you say 100 people are going to attend the wedding and only 10 attended, then your precision is 10 over 100. If only 50 attended, it's 50 over 100. If you say 170 something people are going to have this disease and only 15 attended, only 15 have it. 15 divided by 170 something, and you get your precision. How about your recall? Like I said, I'm going to dwell more on all of these in the next class. So I think we should just stop here. I think we should stop here. So tomorrow we will dwell more on some of these metrics and see how we can improve this model. So tomorrow's class is going to be based on this same notebook. So I'm going to upload this notebook to GitHub, where we can download it and practice with it. Do you have any question? Any question? Okay, no question. So, but I want to ask, the approach I used today, building, I'm just trying to get a feedback for subsequent programs. So running everybody through this process from start without having the notebook prepared before the class, do you think it's a better approach than the other approach? So I want the feedback, please.
Yes, okay. I think it's a better approach